Good afternoon again. My name is Angel Francisco Martinez. I'm an application engineer at Microsoft, and today we're going to do the second training of our ongoing tunnel series, and we're going to focus more on the advances on excavation stages as well as how to extract results once we've finished the analysis, what we call the post-processor. So I'll do a brief introduction and then we will go into setting up the case that we did last week, but now excavating by stages. And then I'll push the boundary a little on that and do a different demo on a tunnel with several connections, not just a straight tunnel, to make it more clear how construction stages really gives us opens the window now for tunneling into very complicated cases. And then at the end we'll do we'll spend some time on the features, the post-processing features, as we call it, to extract the results during this uh, type of analysis. So just very briefly again, we are Midas. We are the #1 developers of civil engineering software around the world. We're kind of coming at you live from our New York City office. But you can see on the map on the top right, we have branch offices around the world, our headquarters being in Seoul, South Korea. So last time we've been talking about the different methods for analyzing tunnels, for designing tunnels. One perspective or one point of view is from the structural side, where you can use springs to model the behavior of the soil, approximate the linear behavior of the soil, and you basically end up just applying loads to the tunnel and determining if, based on the stresses, based on the demands from the members, you can more or less determine what the shape and the, let's say, lining thickness would more or less be. And you can get a decent approximation by this method. It's relatively simple. However, as we've been talking about, from the geotip perspective, it's maybe too simplistic, and we need to consider the ground elements either by 2D, which is a much, at least it's a big step forward from the previous method, because you can now capture the non-linear behavior of the soil conditions. You can also now start to consider the excavation method if you're doing it, full face cut, bench cut, or any other kind of irregular cut you want to do of the tunnel. And as you can see, you can start to also at least determine some of the terrain conditions and strata layer conditions. And then beyond that, if you then push the boundary to 3D, you can now also start to determine the excavation stages or the excavation advances, how far, not just the cut method, but how far each stage should be, what the you know irregularities might be, and once you're in 3D, you can really get into the very realistic simulation of anything you need to consider for the tunnels, like connections or terrain, etc. So the big benefit of once you start modeling in 3D is that you can accurately represent not just the properties of the ground, but also how it's going to behave, especially during the excavation process, since we know that we need to be able to determine the deformations or displacements in all three vectors, all three axes. Something that's, I would say, the biggest limitation to modeling in 2D is that once you start to have your subway stations or parallel tunnels with connections, or you have to have an exit shaft with a gallery and connecting to the tunnel or nearby adjacent structures, then it becomes really tricky to approximate that by slices, by 2D models. And 3D is really when it comes into play. But of course, you can imagine now this starts to become a little tedious and intimidating, since it can easily become hundreds of stages in the construction process, and that could end up taking a long time. So that's part of the reason that 3D modeling is perhaps reserved for more advanced cases, and it has its limitations in terms of the computation time and computation setup, or time to set up relative to the other methods. So we'll see that in the end, each method has its own benefits. The more complex you get, the more information you can get out of it. And today we're going to try to show you some techniques that we have, or tools that we have, so that even modeling something as seemingly difficult as a 3D tunnel with connections can become a little faster, a little less stressful or difficult to set up. We saw last week as well the basically an example following the sequence for a static case. We didn't go into the excavation stages, but if you recall, the most of the time-consuming aspect of modeling in 3D will be split between setting up the geometry of the model, and in 3D we have tools now that you can consider for even importing boring hole data as well as topography or terrain surface information. And then we went through the process of extruding a tunnel face, making sure everything is connected, meshing it, applying our boundary conditions and our loads. And in last week's case, as we said, we just did a very simple static analysis case. So we'll see as a launching point from here, we'll take last week's case and we'll focus more now on this method or on this part, which is setting up the analysis. And of course, we're not going to set it up to be in construction stages. And so the premise being that once you start once you're working on a more advanced project, you really do want to be able to make sure that every one of the stages you're able to accurately reflect what's happening in terms of stresses on the ground, the potential failures of the ground, how are the support systems in place, what the sequence should be, how far should you excavate, how much reinforcement or support system needs to be in place. Even for some kinds of analysis, the duration of each stage, if you need to consider settlement on a softer ground or dewatering, draining in certain, preparing the ground for the project, all that can be incorporated into the stage analysis. And that's why it really gives you the most accurate approximation of what's going to happen in your project. So again, going back as a starting point, we'll look at last week's example. We focused on setting up the model, and to make it simple, we only divided the tunnel into 4 main segments. So we focused on meshing the 3D, how to get the lining, the supports like the rock bolts. But then we simulated just a static case where, let's say it was a long term after the tunnel had been there for a while, more or less what the stresses will look like on the lining, maybe the ground conditions and such. But because it was a static case, there was no real reflection on anything, or the main focus of the results are clearly on the terrain, the slope in this particular shape or this particular model. And we see that reflected, for displacements of the ground. If we were only going to show, let's say, displacements or deformations on the lining, we also see a concentration toward the middle back of the tunnel, which would be reflective against from the terrain. However, that doesn't give us as much information as we would need in terms of preparing for the construction process, since just like bridges, the tunnels are also very vulnerable during the construction process. So we want to be able to inspect that. We want to be able to make sure that we're going, our excavation stage doesn't go too far. The ground can support itself as, we're predicting the number of stages we're going to need to excavate and such. So what we're going to do is we're going to open up the model again we had from last week and start setting up the cases. In Midas, we can set up construction stages for the following types of analysis: stress, seepage, semi-coupled, which is basically you can alternate between stages and change the pore pressure or create some sort of seepage condition. We can also do consolidation analysis in stages, and then even stress analysis with a time history, like a dynamic analysis at one of the stages or the last stage. We will just focus on a stress analysis for this time. And we'll be first 2 stages actually are just initializing the model. And then we'll start excavating each subsequent stage, excavating one phase, and then the stage after that, activating the support system, as we see here in red. I'll also point out some of these other features that we have here for options, like changing the water level table and potentially even activating what would be the load distribution factor, which allows you to distribute the internal forces of what's being deactivated, in this case, the excavation of the tunnel, into several stages. And then we will just kind of continue repeatedly doing the same, deactivating, basically simulating an advancing of the excavation while simultaneously activating the support system from the previous section until we get to the end. So let's just open up the model to show you how to set up this kind of sequence, and then we'll set up the analysis case and inspect the results. But as you can already see, they start to look very different since now we cleared all the displacements from the terrain, all the internal stresses or initial stresses due to the terrain, and we just want to focus on what's happening due to our construction process. So here's last week's model. If you recall, we had a water table that we selected to be following the surface of let's call it here the blue layer, the second strata layer. And we had already also applied all our boundary conditions. In this case, the load is only gravity, the self-weight. And we had created already also the support system, the lining. Last week, we just kind of made all the rock bolts grouped together into a single set. And that was fine. We could get away with that because we were just doing a static analysis case. There was no sequence to the rock bolts being activated. Everything was just activated or was already considered to be there. However, I did go back and just kind of organized it a little bit and started grouping the rock bolts by sections. So, in the construction stages, we can activate them in the correct sequence. So what starts to become really important for construction stage analysis is that you very clearly not just name your sets, but also give a number as a reference to yourself of the sequence of how these might be activated or deactivated. So you see here that we have all of them have a 1, 2, 3, 4 that correspond to the stages of the excavation and installation of the support system. So this would be, let's say we're ready to start the analysis case for excavation in stages. So we would go to our tab. In this case, either of these tabs have the same setup for construction stage, either of these two. So we're going to first tell the program how or what type of analysis we're going to be running in terms of stages, and we want to select the first option, which is stress. We're only going to look at the stresses in this case, and I'll click Add. From here, I will then select it from the list. The program doesn't know if you're going to keep adding more stages, and in this case, we're done. So I select the one from the list that I created, and now I have a chance to define what these construction stages are going to be. And that'll prompt this window. This window is similar to what we did for analysis case, except that we have now an additional window called deactivate data. And that's basically how you can simulate, by dragging and dropping, you can simulate what would be an excavation or a removal of a set from the model. But in order for that to happen, we first have to set up the initial conditions. What's already in the first stage basically is what's on the field or what's happening before any of the project starts. So we're gonna start dragging and dropping what are the sets of the ground as well as the sets of the inside of the tunnel, but not the support systems yet. So this would be the initial stage. One trick that we can do to keep track of this visually is change this option down here called show data to activate, and we see that nothing has been activated yet, so that's why there's nothing shown. But as I start to drag and drop the parts of the tunnels that are to be excavated, they start to appear on the screen. So this is a trick to keep track of everything that's happening in case you're visually missing something. We'll also activate drag and drop the loads and the boundary conditions. In the first stage, we would also start the definition of the water table or the water level in this case. Since I selected it from the drop-down menu, this being the global coordinate system, if it's under none, I will now select in my table. I just basically want to use this as a value of 1 to tell the program I want the input that was generated to be exactly as I left it. Had I given this a higher value, it becomes a multiplier, or lower value, it becomes like a divider of it. So we'll leave that at 1. And the other thing we're going to do is we're going to clear the displacement. So just like we saw in the static case in the previous example, most of the internal stresses or reflection of the displacements were due to the shape of the terrain itself. The self-weight of it is going to push some of the terrain, create some internal stresses in it. We want to clear that because we only want the results to be focused on what is in this case, excavation of the project. we'll go to the new stage, and this will be a null stage, and nothing's going to happen in the stage except that, again, we want to clear the displacement. This is necessary when your terrain has a slope. Had our model been just a completely horizontal soil layers, we wouldn't need a second null stage. But because we are running a stage analysis on a slope, and we're going to activate the K-naught coefficient in the end, which is basically to consider the lateral earth pressure, that creates additional stresses that need to be cleared, and it needs a second stage to be basically a null stage to take care of that. So we have stage 1 and stage 2. Recall stage 1 just set up everything in the models, and stage 2 is a necessary null stage for our given terrain. So now we get into stage 3, and this will be the first excavation. And I'm going to drag and drop this set, excavation 1, all the way to the deactivate data. And you'll notice now if I spin this a little more, it's reflected in the model. So this first stage is, we're simulating the excavation. And as I had shown in the slide, there are now options. For instance, here we could activate this load distribution factor. If we wanted the stresses from this excavation not to be completely accounted for in this first stage, we can say, let's say, only 40% of this internal forces to be considered in this stage, 30% in the following stage, and 30% in the stage after that. So that's one way to do this, or that's how you would do that option in the program. So that's excavation 1. Next stage, this would be the second excavation. So we drag and drop the second set, and you see a deactivate there. But now we're gonna simulate installing the first support system as well as the the lining and the rock bolts. Continue, and this at this point almost becomes repetitive. We're just advancing one stage at a time and activating the support system for the the stage or the previous excavation. So this is something we can do manual for this example because it's relatively few stages. We see there now we've completely excavated the tunnel for our model, hence why we originally in this previous set had done a minimal for the number of divisions of the tunnel to keep this relatively simple. And then this can just be the last stage or the support system, which we basically just activate. There's nothing more to excavate. We're just installing the last support system, which is the lining for and the rock bolts for. One last thing that we can also specify in construction stage analysis is, if we like, we can also, apart from the stress, we can also tell the program that in that particular stage or any of the previous stages to also give us a factor of safety to run a slope stability analysis, which in this case might be appropriate since we are excavating a tunnel in a slope. So you cannot tell the program without having to create a separate case to consider all the stresses along the construction process into that slope stability analysis. So once we set that case up, we would just then tell the program that we need to run that type of analysis. We set up the stages, but now we tell it that the analysis case, analysis tab, and then I went to general. The analysis case is going to be the third option, construction stage. And in the analysis control, we would be able to tell the program initialize this, the stresses in stage number 1. This is mostly for cases where you might have a seepage analysis in the first stage, and you're initializing your model with the pore pressure distribution, but you don't actually start any of the stress considerations into the following stage. So that's where you'll be able to tell the program, start its stresses in such case. In this case, we'll do it in stage 1, and we'll also tell the program that we want to consider the K-naught condition, the lateral earth pressure, and to apply the water pressure from the water table automatically as a load to the structures. And we would be able to, or we would be ready to run it. We would be now running only the second case, since the linear static analysis was something we did last time. However, in this case, to briefly save a little time, let's just say that I've opened the model, or I finished running the model. Oh, one last thing that I might have missed in mentioning is that in the stage of the first excavation, we also redefine the water level table. You can see it now here that I I activated this option again and basically gave it a different height. This time I just said 0. That's in relative to the global coordinate system. If I activate it here, you'll see that we are in that plane. And as I said, if you're not selecting a level from previous defined geometry, this becomes global coordinates. And so hence why 0 here would make this completely along the plane of the origin. So this is a very rustic way of simulating a previous dewatering process. We didn't do a coupled analysis. If you really wanted to get into the details, you could actually start defining seepage boundary conditions and creating what would be a seepage analysis, a flow of water, and you could define a lot more control into that process. In this case, we're taking a big assumption and just saying let's just say that between stages the dewatering occur, and now we can consider that the water pore pressure is below this table. So having done that, these are the same stages, and we ran the analysis. We would now look at the results. The bigger difference now is that our post processor, the software, is now showing us results grouped by stage. And I can expand each stage and see all the results. So we see that between stage excavation 1 and stage excavation 2, we have different or additional options for results. These are only ground results, but once we install structure support system, we now have results for the shell elements, which is the lining, and the truss elements, which are the rock bolts. Other differences now would be, let's say, looking at displacements. We can see the progress of this during the construction process. And we can see the navigation if we wanted to, as well as in the member forces. With this bar down here, we can see the construction process. I can control with my keyboard as I'm advancing till I get to the end. And we can also inspect other things like forces and such. So all depending on, here as well, at the very end, if we remember, we said we applied a slope stability analysis. So these two have the same name. This is the last stage, which is the support, and this is the stage support SRM. So this includes a factor of safety and would give us a potential plane of failure on the slope as well as other results. So there we would see a little more accurately. Of course, I think this layer is rock, and this is supposed to be weathered rock. So the concentration of the failure potentially is as expected on the top layer, and it doesn't really seem to be affecting the tunnel. So we would, consider that this might not be such a worrisome aspect in terms of the terrain having an issue due to the excavation. But again, we would be able to, we'll focus more now on the second example of how to extract these results now that you want to inspect the construction process, not just the final stage results. So moving forward, you can start to see that, in our very simple case, we only had, a couple stages, so we were able to do it manually. But this is going to start to become tedious and inefficient if you're going beyond, a very simple or a couple stages. Once you get into, something like a bench cut excavation where you're removing sections of the tunnel at a time, not just the full face, this can easily shoot up to hundreds of stages. So for that, program Midas has a wizard we call the stage wizard, which allows you to set up rules on a table. So again, what's important is that your mesh sets in the workstream are organized with, in this case, we put a little hashtag to represent number, so that they're organized with a number associated to them and in the name, and that number is in the correct sequence of what's going to be excavated, so that you can set up a rule such as, in this case, it's either A or R, which means remove or activate. So I would select from the table my mesh sets regarding to tunnels, which means in this case the tunnels to be excavated. Remove them starting, let's say, in stage 1, and then do every 2 stages after that. So we would see it down here, as a rule, stage 1, remove tunnel number 1, stage 3, remove tunnel number 2, stage 5, remove tunnel number 3. essentially what we were doing in the other case manually, this would be just now setting it up for us. And similarly for the support elements, A becomes activate. So both the shotcrete and the rock bolts, we would tell it starting in stage 2 and every 2 stages, I want you to start activating the rock bolts in the correct sequence. So we would see that now reflected here in this table. So basically these two correspond to these 2 stages right here. So being able to first remove and then the following stage activate the first set of rock bolts and shotcretes, and then jump to stage 4, activate the second set, stage 6, activate the, and so hence in these kind of cases where it can become, the sequence becomes repetitive, this table will save you a lot of time. And you can just, once you set this up, again, in this example is going up to 10 stages, but this can become hundreds of stages. So that's one way to do it through the wizard. We do have an alternative method, which is to auto-generate the stages by telling the program manually based on what you have activated on the screen. So here I'm setting up the model, and I'm going to do by defining auto stage. So every time I click auto set, the program considers whatever's on the screen as one stage. So this is the initial stage. And I can now start in my work tree deactivating, let's say this is simulating the first excavation. So I click auto set. I then follow up by activating the support system for that tunnel. So I click auto set again. That's a new stage. I go back now and deactivate another set, and I click auto set. So I'm now simulating that excavation. And the following stage would be turning on the support systems for that one. And I go back to clicking auto set again. And I finally now, let's say, excavate the last tunnel. That's one stage, auto set, and its installation of its support system being the last stage. So I click auto set one more time. So that's an alternative of you. That might be more appropriate for a 2D case though, but the program again will allow you to set that up instead of dragging and dropping. It allows you to set it up by just creating the stages and clicking auto set on the model. And once you did that, you could verify. We have another thing before you run the analysis, even if whichever method you did to create the stages, we have a tool called Stage Simulator that would allow you to verify the sequence. So for instance, this would be simulating a TBM machine, a TBM excavation, where the rock is being excavated. This represents the shield. These are the support rings. And then this is the grouting that's injected at the very end. So we would be able to verify that the sequence is correct. And I mean, you would be able to create simulations as well for the results. But of course, this is before the analysis is run, not after, which potentially would save you time of finding an error beforehand. Alternatively, one other tool that we have that's also called Wizard, and this one is very useful for tunnels, is the Tunnel Wizard. So this allows us to create, so long as your tunnel is straight, this allows you to create a whole 3D model within a few tabs and just be able to almost be ready to run the analysis. So the first couple tabs, the first tab would be called General, and that would be where you determine or you tell the program number of tunnels and let's say the excavation method or the cut method. So if it's full face or bench cut, or you would select from the menu. So that would be the first tab, and you would specify the property for the tunnel section being excavated. The second tab would then be the support system, in this case the shotcrete, and you can even give it multiple materials. Let's say when it's first installed or while it's still soft, and then after it's hardened. So you can give multiple material properties for the shotcrete, and also the rock bolts. So you can specify the number of rock bolts, the length, and the distribution of the rock bolts. So this is tab number 2. The third tab, excavation tab, would be then, as the name implies, determining the excavation, if it's a one-way or if it's being excavated from both directions and it meets in the middle. Sorry. And also the advancement of the excavation. So in this case, you would tell it there's going to be 30 excavation stages, and it's going to be every 2 meters or every 2 feet, or depending on your units. And the program will then generate this table for you. And if you wanted to, you can tell it to automatically generate the spacing of the rock bolts to be in the middle of the lining, or in between the excavation spaces. So you see how through these simple tabs, we created a lot of information about the tunnel project in 3D, relatively easy. And then the last tab would just be giving it information about the spacing of or the location of the tunnels relative to the terrain. So how far down, how far centered general to the model or relative to the model. And if you wanted to, you can make it just to be a square model, completely flat, or if you wanted to consider now information about the terrain, you can either by a very simple table format, just kind of type in these values to give it, let's say for one of the strata layers, change the location of the surface in both axes. Or like we did in last example, you can also import grids with information about elevation. So you could tell that I have a grid of data from 11 by 11 with the information of elevations, and you would be setting up information about the terrain as well as the size of the mesh distribution, and the elements or materials being used. And with that, you would be able to be ready to run the model. And once you're running the analysis, the differences in results for the terrain or the support system, as well as the actual forces. So we're going to start to look now one different example, but then we'll jump into all these different methods of cutting into the area of the tunnel that we're interested in, extracting nodes, generating graphs, and such. So let me jump into a more advanced example, not using the wizard, but a tunnel with 3 connections. If you allow me here, it's going to be, this is a tutorial that we have. So here, I'm going to start by drawing. The first part will be, I'm going to draw the terrain surface, create the rectangle of what's going to be the ground. So I'm giving it, in this case, by dimensions. It's a 100 by 61 rectangle. And then I'm going to draw the face of the first tunnel. So similarly to what we did last time, we give the dimensions of the radius, we select the tunnel type, and include, in this case, the rock bolts. We see it there that the center of the tunnel is at the origin. However, I actually want the base of my tunnel to be at the origin, not the center. So I'm going to move this up. And this method is by 2-point vectors. So I select the base of my tunnel, and then I give it the ending coordinates. And the program will calculate the distance for me. And once I click OK, we see that everything shift up. Now I'm going to draw the passage tunnel. It's going to be an intersection of my tunnel. So what I did is I clicked on the work table, or in the tree menu, the work plane that's perpendicular, which is now the CY plane. And I'm giving a new dimensions of my tunnel. This is going to have a smaller size and a different rock pattern distribution. So again, this is the passage tunnel, and it's completely perpendicular to the original tunnel. We see here now, if I spin my model a little bit, I can see the new drawing. So again, for them to kind of line up, I want both of the bases to be at the origin. So I'm going to select the curves of this new tunnel, and again, move them by the vector option. So I click on the base of my tunnel, and then once that's engaged, I give it the final location, which is by coordinates 0, 0, 0. I tell it to calculate the distance, and the program will shift or translate, as it's referred to, the tunnel to its correct section. So now, once I have these drawings, I'm going to start creating the solids by extruding. So first I select the terrain, and I tell it I'm extruding it 45 meters in the Y direction. And I repeat the process for the first tunnel, the main tunnel. I select the boundary of the tunnel. Again, I select the Y-axis, and I give it the same distance, 45. I can verify it that way. And now I'm going to extrude the passage tunnel in the X-axis, which is perpendicular, and now I'm telling it 20 meters. In this case, as we said, in the X. And the last is going to be the shaft, the exit shaft. For this, I'm just going to draw or create a cylinder solid. So I know the coordinate location. I'm telling it the dimensions. It's a 40 meter shaft with a diameter of 5. And I can actually draw it into my model and it has an option to lock things into place. So these tunnels have now connected at the base. Now I'm telling the program this tunnel is inside of this solid, and repeating the process for the other sections. So the tunnel shaft and the tunnel passage connection are actually going to be just half of the simulation. We're assuming this is a T connection and it's symmetric. So I don't need to do the full model. I can actually just focus on half. So here I'm dividing basically, or telling the program all these three tunnels are going to be connected to each other. I want you to divide the remaining terrain by these geometries, as well as these geometries if they intersect to each other. So if I change here that transparency, you can see now that the program is recognizing the main tunnel, of course, it's fully there. The passage and the vertical shaft are, as we said, only half because we consider this to be completely symmetrical, and that actually in the long run save time in the analysis run. So what I want to start doing now is start organizing my work tree. As we said, it's critical for construction stage analysis that it's very clear where everything is grouped and together. So I assign names to my folders, and now by dragging and dropping, I can put the geometries into the corresponding set. So here I'm just kind of activating and deactivating to verify this. What I'm going to start doing now is here I brought the work plane back to the original, which is the CX plane. I'm going to draw a rectangle to use to divide basically the spacing excavations of the main tunnel. So I drew a face just big enough to cover the area or the face of the tunnel. And now I'm going to select that face and make copies of it along the y-axis. And I can tell it either to make uniform copies, uniform spacing, let's say 3 meters 14 times, as we saw here. And once I click OK, I can get rid of the first face since it won't divide anything. And I can now specifically say, okay, this tunnel will be divided, this solid, divided up by these faces, these 14 faces that I have just created. And because I've started to group all my geometries, it's easy to find them in the work tree. I'm also telling it that if these divisions happen to be touching, let's say that other passing tunnel, I want you to reflect that division in the geometry of the other sections. So now I change again my plane, my work planes around. So the next thing is we're going to do the same for the passage tunnel. I'm going to draw a face just big enough to cover, of course, both faces of the complete face of the tunnel. In this case, it's basically just half. And again, we're going to make copies of this plane or the surface, this time non-uniform. So I can specify also by separating by comma. So I can tell it at 9 meters, and then after that, 3 meters further, so that's why the comma is there, create these two surfaces. So it doesn't have to be uniform. You have a lot of control in that distribution. We delete this first surface since it's actually not part of or it's not going to divide anything. And we go back to dividing now the passage by these two new faces we created. And again, we can tell the program, I'm dividing this solid in the remaining, or let's say for the ground, I want you to be also making those divisions in the matching faces. And the last, of course, would be for the vertical shaft. Once more, we move the work plane, in this case to the CY axis. We generate a rectangular face that's just big enough to cover the tunnel shaft. And then again, we're going to make copies this time in the Z axis, in the vertical direction, to do these divisions. And this time will again be non-uniform. So we're doing it at 6 meters, then 7 meters, then 6 meters, and 6 meters, and 5. And that extra surface is deleted. Now we go back to dividing the vertical shaft, selecting the faces. And once more, we're just letting the program know if these divisions, of course, are going to be touching the terrain, but if they also happen to be touching other solids like the other tunnel, I want you to consider that division. And now one last time, this time we're gonna just divide the terrain to create the strata layers. So I'm drawing one surface once more on the X, Y plane, and I'm gonna make copies of it in the vertical direction at 19 and 11 meters moving up. And these will be used to generate the strata layers. In this case, we're making an assumption that the terrain is completely flat and the strata layers are completely flat. And so we divide now the solid terrain by these surfaces. So we give it a quick inspection. We can now see the divisions. What I'm going to start doing now is I'm going to draw my rock bolts. So we drew the rock bolts in the original tunnel faces, but because the shaft was just drawn as a cylinder, I have to manually go back and draw the rock bolts. So what I did is I just drew one line to represent the first rock bolt, and then I'm going to make copies of it around the z-axis with the location centered at my vertical shaft. And so I can specify, angles, first at 15 degrees, and then after that, give me 5 more at every 30 degrees. And we can see here now that extra one is deleted, but I've now made copies of this first initial one-line element to match my distribution of rock bolts for that tunnel shaft. So now I'm ready to mesh. So I'm going to use this, or we have this handy tool called size control that I can pre-specify a size of mesh at different boundaries. For instance, 8 meter spacing or large spacing for the outer boundaries of my model. And let's say I want to have a closer distribution of, or more control of the distribution of size of elements as I'm approaching the center of my tunnel. So we have this option called linear grading. I can give it a starting size and an ending size that are different, and we see an arrow, directional arrow. We'll let the program then have that spacing, and I can do the inverse depending on which arrow or which direction the arrow is pointing. And I can also make it so that it's not just one single direction, but it can be symmetrical seating. So I can say starting at one size and near the middle being a smaller size. So there's all these different options. I'm just showing you alternatives to controlling the size of the mesh around your model even before you start to mesh. And so we're now ready to go into the 3D meshing. I will start by first meshing the main tunnel. I'll give it a global size of 2, and I'm using the hybrid option. And here I select the material. So this is my main tunnel. And because I selected it from the front face, everything that I generated in the rectangle was captured. So all of the main tunnel was meshed. Now moving on to manually selecting the 3 passage tunnels. And then lastly, I will generate a rectangle to select what are the vertical shaft sets. So I give them all the same size. And now I'll start meshing the layers. One can, mesh one by one and assign the appropriate material, or you can always mesh them all together and then go back and modify the material assigned to them in the workstream. So here we'll just give them all a uniform size and mesh them in what we call mesh in the same step or parallel. So we have essentially finished meshing our model. What we want to do now is, these are the excavations or the tunnel excavations, but we also want to now mesh the support system, the lining. So for that, there's different ways to do it. We consider the easiest way to do it is to extract the element from the surfaces of the already meshed tunnel sections. And it's much easier to select faces of a geometry than the elements. The program does allow you to just activate the geometry of your solids and then extract by assigning the material property, in this case, the thickness of our lining, to this mesh that was created from the solids. So now if I hide the geometries, this looks like I have created solids, but they're actually shells. They're hollow inside. So I need to get rid of the extra faces, the exit, and of course this is the faces corresponding to the models that don't match. So there's no lining, there's no floor slab, and we're also deleting at the end of the tunnel, so that when I spin it, you see that only the supporting lining system is retained. And now I'm gonna go and mesh my rock bolts. So this is a 1D mesh. These are 1D elements. So I'm selecting here and deactivating the tunnel section and only meshing the rock bolts. However, if we wanted to have a frame support system, then you could also mesh the tunnel section and assign it like a beam property to include as additional support, not just the lining. So last week we made copies of the geometry of the rock bolt and then mesh them in steps. What we can do here is also just first mesh and then make copies of the meshes of the rock bolts. So here I'm telling it the distance at 1.5 and then every 3 meters 14 times. And I want to make sure that I specify the name in the works tree. So this is what the rock bolt distribution will look like after I've made copies of the mesh. And I delete the initial one. And I'm going to do the same for the passage. So I change my plane view to the ZY plane. I select the edges. These are extra, so I'm actually going to delete. And now I'm going to mesh the other half, the remaining bolts. And I assign the property and mesh. And again, we are going to make copies of this case along the x-axis. That's what I'm spinning here and selecting, and it's going to be non-uniform. So I'm going to tell it at 7 meters, and then after that, twice at every 3.5 meters. And this will be the passage rock bolts that we see the preview there. So we're going to have 3 sets in the end. And we delete the original. And then lastly, we'll do this one more time for the vertical shaft. So I select my rock bolts, I mesh them, I assign the material. And then I'm going to make copies under the command translate. I select the C-axis, and again, non-uniform copies. So I tell it 3.5 meters, and then every 6, 6.5, 6, 5.5, and then lastly 4.8. So I'm specifying basically how far each rock bolt location is going to be. And these are the vertical shaft rock bolts, or RV. So we are essentially done with meshing. But what I wanted to do now is start to organize them to be, because they're not necessarily meshed in the right order. So by using this command called rename, I can specify the program, all right, all my main tunnels along the y-axis, I want them to be in ascending order. And I assign a name and a hashtag in front of it. So start with number 1 and then, with 20 or whatever. For my passage tunnel, it's actually along the x-axis ascending. And then for my vertical tunnels, it's actually going to be in the C-axis, but it's going to be descending. So it's going to be excavated from top to bottom. So we give the name and always end with a hashtag, and that allows the program to specify the number behind it. So we repeat the same process for the main tunnels. This is ascending in the y-axis. For the passage, it's going to be descending in the x-axis. And then for the vertical shaft, it's going to be descending in the z-axis. So we put vertical shaft, rock bolts, hashtag, start with number 1 and end in the last set. So using this rename, we're going to do this one more time for the lining. I select the lining for the main tunnel. I tell it along the y-axis, it's going to be ascending or increasing. And this is my main tunnel, shotcrete, hashtag, start with number 1. And then for these 3, it's along the x-axis descending, so that means it's from left to right. Sorry, from right to left. And then the vertical shaft. The C-axis descending, so from top to bottom is going to be activated. Vertical shaft, shotcrete, hashtag, start with number 1. And you can see now this is the fundamental part to setting up the model so that the tunnel or the excavation wizard or construction stage wizard, that table that we're going to be using, can properly apply those rules. And the last thing is we're just specifying the names of the layers, and we could have also modified the materials if we wanted to, assign to each. We're now applying the load. In this case, we're going to keep it simple for time purposes, and we're just going to say just self-weight, and the constraints are just the auto boundary conditions. They're going to be applied automatically. So the program will identify the faces and apply the corresponding constraints. So now we're ready to set up the stages. I just first have to tell the program what type of construction stage analysis, in this case, just stress, and then I can jump into the wizard. So if you recall what this system is, you select the set, and then you tell it if you're activating or removing it, and then you tell it where to start and how much to advance. So we're starting with the vertical shaft tunnels, and we're going to remove them, starting in stage 1 and advancing one stage at a time. The next will be activating the support system. That's the shotcrete and the rock bolts for the vertical shaft. So we told it start at stage 2 and advance one stage at a time. We're now removing or excavating the passage tunnel starting in stage 8 and activating its support systems, both of them starting in stage 9. And the last is the main tunnel to be removed or excavated starting in stage 12, and the support systems activated the stage 13 after that. And they're all advancing one stage at a time. So you just kind of more or less have to keep track, but once you generate the table, it becomes more clear what's visually happening in the process, so that each removal is following a subsequent stage of support system previously. And the last thing we gotta do is we gotta set things up for the IS, or the initial stage. So from this group worktree, I'm dragging and dropping everything that needs to be considered in the very first stage, kind of like what we did in the other case manually. Just make sure that everything is in place before it can be excavated. And now the program has automatically created for me all my analysis, in this case 28 stages, and I just tell it that the initial stage, clear the displacements. If I wanted to define the water table, I would also be able to modify it or make any modifications there. But you've seen that I've now very easily set up this case that has 30 plus stages. And here, if I want to consider just the stresses, I'm not going to apply the lateral earth pressure condition, the K-naught condition. And I am now ready to run the analysis. So jumping into the analysis finished being run, again, we can inspect now all 27 stages. If I expand on them, I can see the progression of the results. Initial stage, of course, has nothing. This is with the deformation exaggerated. I can actually click up here to give me the real deformation. We can switch the units here to any unit we want, even after running the analysis. So here, it's in millimeters. We can make it inches. So it doesn't matter how you set up even your values for your loads or your materials. At any point after you run the analysis, or even during the process, you can switch the units up down here. So here there's a bar at the in the boundary between my output window and my main window. And again, with that, if I hold onto it in the mouse, I can drag it to the right to see the progress of the analysis. I can also press on my keyboard. If I press it once in my keyboard, if I go left or if I go right, I can also see the progress of the analysis. And it'll stay locked onto the type of result you selected, but that could be updated to any kind of result you want to see, like the moments on my lining. I can also see the progress of that during the construction process, etc. So we can now go back to the presentation and start looking at some of the different output methods that we can use for advanced output, especially for construction stage analyses. So as I mentioned, in this model, if you recall, we were only considering the full tunnel, the main tunnel, and for the passage and the vertical shaft, we considered it to be symmetrical, and hence we reduced a lot of the stage time and number of elements by just doing half. But the program does allow this option to look at the mirror image, not necessarily generate all the elements, but in the post processor, once you're looking at the results, if your model is symmetrical, it would allow you to create a complete mirror image, and you can now inspect the results as if you were looking at the full case. In this case, though, this will follow the same sequence, just that these tunnels will now be excavating away from each other in the process. But you can leave this on and look at any results you want, including the support systems, as well as using now some more advanced features like what we call the ISO value surface or volume. So you can clear out and only leave activated volumes of material or whatever it is based on a range of values you're describing. So let's say that I only want to concentrate on anything that's potentially deforming more than 3, in this case, millimeters. By applying this option, I'm isolating and focusing exactly on the area of interest. So let's get to this point from our current model. So here's our existing model. I'm going to switch the results to displacements. So you see, I mean, we can more or less see what's happening. And because we set up the model to be symmetrical, it's already like we did a cut of the plane. Up here, there's an option called clipping plane. So that would allow me to create additional, and I can create, I think, up to 6 at the same time, additional clipping planes if I wanted to look inside the model. What the other thing that we're going to start doing then is, right next to that command is the mirror plane. And I would just specify to the program along which plane, in my case, it's going to be the Y plane, I want the model to be symmetrical. And so if I go here now, you see that this has been created symmetrically. And even though I can't really see much unless I kind of get to the last stage, and that'll kind of more or less gives us the final shape, by using this command of ISO value surface, depending on the result that's activated, I can control the range of values to be generated. And so this allows me to more clearly see the areas of interest, the areas of concentration for my project. Or it can be the inverse, to keep the lower part and kind of retain that aspect. So it really does start to give you a lot of different methods of seeing your results. Beyond that, once you have this activated, well, we saw this result for what was, ranges of values, but we could also do that for safety factors of materials, and we can then compare that to the plasticity or the material status itself. So for 2D, here we're comparing, the plastic failures versus what we're seeing factors of safety below 1 for the material to activate only those volumes of terrain. We can also now start using our other more advanced features, especially for construction stage analysis, to generate graphs, to get results, extract results along the entire process of the model, and either graph it internally or send to Excel. So going back to the model, if, for instance, let's say I wanted to get the maximum displacements along the entire process, I would click on Extract, select the type of result, let's say displacements, let's say total displacements. This would allow me to select which stages to consider in the analysis. Here, I would be able to select nodes of interest along the way, and they can be many. The more there are, the more data tables values are going to be generated in the table. Or I can simply just tell it to show me the max or the min values and generate a table. And clicking on that, I would be able to get these results on a new tab, and I can select the columns of interest, and I can either send that directly to Excel or tell it to generate a graph. And I can repeatedly do this and get all the tables that I need, or send all the tables that I need to Excel. Some other more advanced results that we could get, had we created seepage conditions, we would be able to determine the flow path. And and if we applied a review boundary to our tunnel face, we would then also be able to tell the program, all right, I want to know how much is seeping into my tunnel, calculate the quantity. And we also have special boundary elements that are called seepage cutoff. You can kind of see the before and after, and this can be for a plane or for 1D element, to kind of control the direction of the potential flow or seepage direction. And then other things that are important if you're working in 3D, well, we saw this earlier, is that we can create animations of our entire analysis. Under the bar that we were using to navigate back and forth, there's a little camera and then a play button that would allow you to generate this type of analysis or this type of animation. And also, if we're doing cuts into, let's say, the division of the tunnel, we were able to use this function called 3D to 2D. So it allows me to select nodes and generate tables specifically from the plane that I've now cut manually. So going back to this, if I was to have as we had done before, cut along the main passage tunnel. I would then also be able to, let's say, add that plane there. Right here under others, right next to extract, there's the 3D to 2D wizard option. And those red buttons represent all the location of the nodes. So if I zoom in, I can start to see the values that I'm starting to generate in this table. And I can also directly act it here to tell me the max and the min. This is for, I guess, really useful for 3D analyses. We're talking here about the seepage, the path, and the flow. We didn't run a time history analysis, but we can generate automatic graphs. And then everything else is just a visual thing. If we want to include the mesh in the view of it, we could click it there. We have the want it to be smooth or fringe, we can change the look. If we want it to look exaggerated deformation of what's happening, or the actual deformation, or just no deformation, that's that output as well. And the last thing is, for tunnels in particular, you can actually even simulate what would be a walkthrough or flight through simulation. You specify a path, and then you can tell it the direction and the speed, and the program will then give you like a virtual tour as if you're going through the tunnel itself. And this is beyond just checking the shape. You can actually select results and reflect that in the simulation. So you can be switching between stresses or displacements through the simulation and inspect, so maybe something that you missed from the other perspective. You'd be able to immediately identify inside the tunnel. So here we're looking at vertical displacements, or the displacements in the y direction. And I would maybe have an idea of like, all right, this intersection here or that part there is maybe tricky, and I need to take a closer look at it. And the last thing is the program. Let's say you get to your final report and you want to send it to somebody. We generate our reports what's called 3D PDF. So you select which results you want to include in the model, and once you send this to somebody by PDF, they don't have to have the program IDAS to inspect the results, but it's almost like if they did. This is a PDF you send by email, and they're able to now rotate the model, inspect the results, if they want to generate their own cuts, if they want to leave comments or such. So you would select which results to include, and you can have as many as you want. Of course, the file gets heavier and heavier, but this is the output in terms of reports for the program, the 3D PDF or dynamic PDF. So in conclusion, tunnels cover such a wide range in terms of options for analysis, because you can decide so many things: the excavation method, the support system, even the type of tunnel. So there's really a lot that needs to be verified. But with finite elements, we can get the most accurate representation, not just of the tunnel, but also of the process, as well as the terrain. And if we needed to include or couple it with other kinds of analysis like seepage or seismic, we can even consider that. So going back to even last week's session, just kind of emphasize 2D does have its benefits. It has many purposes, and one of it, or the main one being, is that it takes less time to set up, and it can give you a very good idea of what's going to happen before you consider that it might be necessary to jump into 3D. So you kind of have to make the decision. If you can idealize or simplify your geometry enough, then 2D might be enough. But you're assuming that the tunnel is, for one, completely straight. There's no intersections, and you're kind of missing that. Whereas with 3D, it's the most accurate way to simulate your terrain as well as the sequence of constructions. But of course, this is going to be a more time-consuming process. And so it's kind of one of those things that you should determine after you've maybe first created the 2D model. Basically, the recommendation is like, don't necessarily assume that you have to always model in 3D. There are cases where 2D will give you a good enough idea, but it's up to the engineer in that respect. So that concludes the main part of the presentation. We do have an assignment for those who want to try it out that we'll be mailing out to you guys. And this will be basically setting up the wizard. So the starting file will already have the materials defined, and you would just have to follow the instructions on the 4 slides that allow you to go through these, each of these tabs. The second tab for the shotcrete, the third tab, excavation, and then just defining the terrain. And you'll be able to set up the model and run it. And this should probably take you 10, 15 minutes. So if you want to get a certification for this whole process, you would just send us the model and a screenshot of one of the results. It can be displacements or forces or whatever to this email. And as a reminder, we have recorded this session and we are going to upload it to our webpage, northamerica.midasusure.com, which is this page right here. So you would just go to review courses and it'll take you to this page. Here you can see from last week's session. And if you were to click on it, you would have the video recording. You would be able to download the slides and the models. In the start model option, we will include the assignment that we're handing out. So if you want to get sort of a certification for tunnel, with our software, you have until the end of the month. But we'll also be sending up a following email with these instructions as well as the demo version for those of you who haven't downloaded it yet. So I will now leave the session up to questions. But thanks again for all your time.